Okay, let's unpack this. We do a lot of deep dives here on the show, and usually when we're prepping for a topic, we're wading through, a stack of dense white papers.
Right. Or we're dissecting some incredibly heavy philosophical treatise.
Yeah, exactly. Or maybe we're looking at quarterly market reports that are just wall-to-wall spreadsheets. We are very used to complexity wrapped in professional jargon.
Mm.
But today, well, today we are looking at something that on the surface seems incredibly, almost deceptively simple.
It really does seem simple at first
Yeah.
glance, but as we often find in science and specifically in physics, the simplest concepts are often where the absolute most chaos is hiding.
I completely agree. So here is the setup for you as you listen today. We have in our hands a chapter from a science textbook.
Mm.
Specifically, it's chapter 12 from a class 6 science curriculum. The title is Electricity and Circuits.
Which is, the standard curriculum for that age group. It is the foundational stuff, the building blocks of modern life, really.
Right. But here is the twist. If we were just reading the publisher's PDF, this would be a very short, very dry, deep dive. But we aren't. We are looking at a scan of a specific student's copy, a student named Aram. And Aram has opinions.
He certainly does. This isn't just a textbook, it's practically a manifesto.
It is a battleground.
Yeah.
He has annotations in every single margin. He has side notes. He has what he calls technological updates. He has these things he labels as lateral thoughts. And frankly, he seems to be operating on a level of enthusiasm and distinct danger that the textbook authors probably didn't anticipate when they wrote this safety guide.
It's such a fascinating juxtaposition. On one hand, you have the dry, structured, very safe language of the educational curriculum, trying to teach basic physics to 12-year-olds. And then in the margins, you have Aram.
Who is talking about full bridge rectifiers.
Exactly. He's talking about watching explosions on YouTube, and he's contemplating the conductivity of air at high voltages.
So that is our mission today. We are going to explore the fundamental physics of electricity, how it works, where it comes from, how we tame it. We're going to do this through the lens of this standard text, but elevated by the chaotic, enthusiastic commentary of Aram. We're going to learn about the circuit, but we're also going to learn a bit about the mind of a young engineer in the making.
I really think we're going to find that Aram actually understands the material better than the book does in some places. I mean, he is actively engaging with the physics, not just memorizing the definitions.
Oh, absolutely. So let's jump right into the initial hook. The source material starts by trying to establish just how ubiquitous electricity is. It lists everything to get the student thinking. Televisions, radios, computers, water purifiers, and then it lists something called a calm cleaner.
I saw that. I stared at that for a good long while. Calm cleaner.
I feel like I need a calm cleaner. Just a device that glides around my house, whispering affirmations, maybe releasing a little lavender scent, lowering the household cortisol levels.
I assume, sadly, that is a typo for vacuum cleaner. Unless there is a massive sector of the appliance market I am woefully unaware of.
Yeah, likely a typo. But the point the text is making definitely stands. Electricity runs metro trains, it runs factories, it runs the pump that gets water to the roof tank. The text defines electricity essentially by what it does. It describes it as a form of energy that gets converted. It becomes sound in a doorbell, heat in a geyser, light in a torch.
And this is the core concept to start with. We often think of electricity as the stuff we buy. But electricity isn't the end product, it's the carrier.
The courier.
Exactly, the courier. It is the most efficient medium we have ever discovered for moving energy from a source like a burning pile of coal or a spinning wind turbine to a load like your toaster. It's the delivery trucks of the universe.
And almost immediately, right next to this definition of energy conversion, we get introduced to Aram's voice. Because while the text is explaining these conversions in very neutral terms, Aram has scribbled a note introducing himself to the reader. Or perhaps just to himself.
It's like a diary entry in a physics book.
He writes, "The section below includes the part my mother taught me, which helped me, I am Aram Smiley Face, understand the topic better."
The smiley face is key there. It sets the tone. He's happy to be here.
He really is. And throughout this text, he references a YouTuber named Electroboom. Now, for anyone listening who might not spend their free time on engineering YouTube, we should probably explain who that is.
Electroboom is a phenomenon. He's an electrical engineer named Mehdi Sadeghdar. He makes videos where he explains complex electronic concepts, but he uses comedy, specifically slapstick, to do it.
Right.
He often, safely but very dramatically, shocks himself, blows up capacitors, or creates sparks to demonstrate what happens when you get the math wrong.
Which explains a lot of Aram's commentary later on. He's learning physics, but he's learning it through the lens of what happens when this goes wrong.
Which is honestly the best way to learn engineering. Engineering is largely the study of failure modes. If you know how to blow it up, you know how to keep it from blowing up.
That makes perfect sense. So we have our roadmap for this deep dive. We're going to cover the source of power, the anatomy of the battery, the evolution of the light bulb, the mechanics of the circuit, and finally, the safety protocols that keep you from, as Aram puts it later, getting fried from the inside.
Let's start at the source. Part 1, the source of power.
The text starts with a very tactile example, the torch, or the flashlight, depending on where you're listening from.
It is a perfect pedagogical starting point because a torch is a self-contained power grid. You don't need to understand transmission lines or step-down transformers yet.
Right.
You have the generator, which is the battery. You have the transmission line, which are the wires inside the case. The load is the bulb. And the control is the switch. It's a micro-universe of physics right in your hand.
The text asks the student to observe the torch. Switch on, bulb glows. Switch off, bulb goes dark.
Yeah.
And it makes this deduction. The working of a torch shows that something must be flowing through the bulb when the torch is switched on.
That something is the electric current. It's interesting how abstract that concept actually is when you first encounter it. You can't see the current, you can't smell it usually, you only see the result, you see the light.
The text mentions that if you want to actually measure this invisible flow, you use a tool called an ammeter.
Right. And to expand on that for a second, what the ammeter is counting is electrons. We are talking about the physical movement of subatomic particles.
Like a microscopic river.
Exactly. In a copper wire, you have atoms that are essentially holding hands, but their outer electrons are very loose. They love to wander. When you apply pressure, which is voltage, those electrons start to drift in one direction. That drift is the current. That is what the ammeter sees.
But then the text zooms out. It asks, where does this electricity come from? If it's not in a torch, where do we get it for the calm cleaner or the metro train?
It lists the big ones, power stations. It mentions they are usually located near rivers, waterfalls, or windy areas.
Why is that? I mean, the text implies it, but doesn't explicitly explain the mechanics of the turbine for a sixth grader.
Well, the text says these are large-scale sources. The implication is that you need mechanical force. To make electricity on a large scale, you generally need to spin a magnet inside a coil of wire.
That's a generator.
That's a generator. To spin that heavy magnet, you need a lot of push. Falling water in a hydroelectric dam or blowing wind against a turbine gives you that push for free.
It also mentions solar panels, which don't spin.
Right, that's the exception. Solar is the photoelectric effect, knocking electrons loose directly with light photons, but most of the grid is still spinning magnets.
But then it pivots back to the portable stuff, the electric cell, the battery. This is where we spend a lot of time in the source material and where Aram gets very, very interested.
The electric cell is a marvel of chemistry. The text notes it was invented by Alessandro Volta, an Italian scientist.
Hence volts.
Hence volts. Volta built the first voltaic pile in 1800. It was stacks of zinc and copper discs separated by brine-soaked cloth.
Wow.
Yeah, it was the first time humans had a steady, continuous flow of charge. Before that, it was just static shocks and lightning.
And Aram jumps in right here.
He does.
The text is explaining the basic structure of a cell. But Aram has a side note. He writes, there are a lot of types of cells like fuel cells, mercury cells, and many other types. My favorite is basic electrochemical cell with zinc and copper.
He has a favorite chemical reaction. That is genuinely endearing.
It is zinc and copper. He's referring to that classic chemistry. Why those two metals?
It's about the desire for electrons. We call it electronegativity. Zinc is a metal that is very generous. It wants to give up its electrons. Copper is a bit more greedy. It wants to take them.
Okay.
So if you put them in a solution that lets ions flow, an electrolyte, the electrons will rush from the zinc to the copper. That rush is the electricity. Aram liking that specific pairing suggests he's probably built one.
Like the potato battery experiment.
Exactly. Or a lemon battery. You stick a galvanized nail, which is coated in zinc, and a copper penny into a lemon. The acid in the lemon acts as the bridge. You can power a small LED or a digital clock with it. I bet Aram has a lemon clock ticking away in his room right now.
What is fascinating here is that the textbook breaks down the anatomy of the commercial cell, the standard AA battery, very clearly. You have a cylindrical container. Inside, there are chemicals. You have a metal cap, which is the positive terminal, and a metal disc, which is the negative terminal.
And it mentions the wrapper, the plastic or rubber cover. The text says this is to insult it.
Insult it. Again with the typos. You call yourself a battery, you're weak.
I really think the editor for this textbook was having a rough day. It definitely means insulate it. But that insulation is critical. The entire metal can of a typical battery is often connected to the negative terminal. If the side touches the positive terminal of another battery, you get a short circuit. The wrapper keeps the flow directed only to the ends.
The core mechanism described is that chemicals inside react to produce current. And this is the sad part of the battery life cycle. When the chemicals are sued up, again, likely used up, the cell stops producing current. It is dead.
This distinction is actually really important, and the text and Aram makes a point of separating the two main types of cells. You have primary and secondary.
Okay, let's unpack that. Primary cells.
Primary cells are the ones you use and discard. The reaction is irreversible. The chemicals change form. They essentially turn into ash inside the battery, and you can't turn them back into their original state.
Right.
The text gives examples like the dry cell used in wall clocks, remote controls, flashlights. Once that chemical magic is done, it's done. You throw it away.
Which creates a massive amount of waste.
Incredible amounts of waste, but they are shelf-stable. They hold their charge for years in a drawer just waiting for you to need them during a power outage.
And then there are secondary cells.
These are the game changers. The reaction is reversible. You can pump energy back in using a charger from the wall to force the electrons back to the starting line. You literally reset the chemistry. These are your accumulators, your storage cells.
This is what runs our entire modern lives now. The text mentions mobile phones, laptops, and interestingly, cars.
Yes, the heavy lead-acid battery in a traditional car is a secondary cell. The alternator recharges it while you drive.
Aram seems to appreciate this distinction. But I love that his favorite is still the basic zinc and copper. It's like he appreciates the vintage classics.
It is the fundamental science. If you understand zinc and copper, you basically understand the lithium-ion battery in a Tesla. It's just scaling up and tweaking the chemistry for more power density.
So we have the power source, we have the battery, now we need to use it. We need to make something happen. This brings us to part 2, light and the evolution of the bulb.
The electric bulb. The text calls it an incident light bulb. It almost certainly means incandescent.
Incident light bulb. It sounds like a bulb that only works when there's an emergency. Quick, turn on the incident bulb.
The text is absolutely riddled with these little typos, but the underlying physics remains solid. It describes the classic structure. You have a transparent glass cover. Inside, a filament.
Made of tungsten.
Tungsten. It is the hero of the 20th century. The text explains the mechanism. Electricity flows through this incredibly thin wire. The wire fights the current, it has high resistance, and that physical struggle creates heat. It gets so hot it glows.
Which is actually kind of violent if you think about it. We are basically torturing a piece of metal until it gives off light.
Precisely. We are heating it to white-hot temperatures, something like 2,500 degrees Celsius. The only reason it doesn't instantly burn up is that there is no oxygen inside the bulb. It is either a vacuum or filled with an inert gas like argon.
And that's why the text mentions the fused bulb. If that tiny filament breaks, if it physically snaps from the heat or from a sudden vibration, the path is broken, the circuit is open, the light dies.
Now, this is where Aram steps in with what he calls a technological update.
I love this part. He is not having it with the ancient history.
He really isn't.
The textbook is describing the tungsten filament bulb. And Aram basically says, okay, boomer.
In so many words, yes.
He writes, bulb used to be fillium net bulb, like what this passage says, but after there came incandescent bulbs, and after that we have lead bulb, like the kind we use today.
He's distinguishing between the generations. He is a bit confused on the terminology filament actually is incandescent, but his overarching timeline is completely correct. We moved from heat-based light to something entirely else.
He goes on to write, it is very power efficient and also powers our screens, so do things on the interwebs, smiley face.
He is making the connection between the light source and the information age. This is profound for a student his age. LEDs, light-emitting diodes, aren't just better light bulbs. They are semiconductors. They are the exact same technology class that makes the computer chip possible.
And he points out they are power efficient. He knows that the old tungsten bulb is mostly just a space heater that happens to make a little bit of light as a byproduct.
Right. An incandescent bulb is about 5% efficient. 95% of the battery power just becomes heat. That's why you burn your hand if you touch an old bulb while it's on. An LED is cold. It converts electricity directly into photons using quantum mechanics. An electron drops into a lower energy hole in the crystal lattice, and pop. Out comes a photon. No heat required.
It shows Aram isn't just memorizing the textbook to pass a test. He's living in the modern world. He looks at the screen in front of him and knows, oh, that's an LED.
He understands that the internet, the interwebs, is visible to us because of this specific technology. No LEDs, no flat-screen smartphones, no ubiquitous mobile internet.
So we have the power, the battery, we have the load, the LED or the tungsten bulb, but we can't just tape them together. Well, I mean, we could, but we need control over it. We need part 3, the circuit, and the switch.
The circuit. The text defines it as a close or complete path.
I really like the visual imagery of the path. If the path is broken, the hikers, the electrons, just can't get through to the other side.
Exactly. Closed means continuous, the torch is on. Open means the path is broken, the torch is off.
The text suggests a hands-on activity here. It tells the student to take 2 cells, tape them together, positive to negative, to create a battery unit.
It's a standard science class experiment. You are creating a series circuit. You physically stack the voltage. 1.5 volts from the first cell plus 1.5 volts from the second cell equals 3 volts of total pushing power.
But Aram has a safety tip here. He writes, "Hi, it's me, Aram," or is it, yes, it is colon. "Make sure your tape is electrical tape so you won't get shock." I've learned my lesson.
I've learned my lesson.
That heavily implies a backstory.
It absolutely implies that Aram tried to tape batteries together with maybe standard Scotch tape or maybe some conductive foil he found in the kitchen, or he just touched the bare metal contacts and got a nasty little zap. He heavily emphasizes electrical tape.
Which connects back to the concept of insulation we talked about earlier. But why electrical tape specifically? Why not masking tape?
Electrical tape is made of vinyl or plastic that is specifically rated to withstand higher voltages and thermal heat. It stretches so you can make a really tight seal around the wires. If you use regular paper tape, it might catch fire if the wire gets hot, or it might not insulate well enough if your voltage gets higher and pushes through it. Aram has probably burned his fingers on a hot wire before and learned the hard way.
Which brings us directly to the switch. The text describes the switch as a device to make or break the circuit. Simple enough. 2 metal contacts. When they touch, current flows. When they separate, it stops.
It lists a few types: tap switch, toggle switch, push button.
But Aram has a lateral thought here. And this is where he shows he is definitely watching Electroboom. This is the moment where the deep dive turns from grade 6 science into graduate level physics.
Read us the note. It is brilliant.
He writes, "A switch, literally, not lateral, my FAV podcast, other than the deep dive, breaks a circuit. It opens the current up and putting air, which is an insulator, into the middle so the circuit can't let current flow through it."
Wait, hold on a second. First of all, did he just reference us? My FAV podcast other than the deep dive?
He did. Aram is a listener of the show.
Aram. Huge shout out to Aram. That is fantastic.
We have officially captured the demographic of genius 6th graders. But seriously, look at the physics he is describing here. He is defining a switch not just as a mechanical stop sign, but as the physical introduction of a new material, air, into the electrical path.
That is a really, really sophisticated way to look at the world. He understands that the gap between the metal contacts isn't empty void space. It is filled with atmospheric air, and air is an insulator. That is why the spark doesn't just jump across the gap when you flip the light switch. Usually. Because Aram continues. He says, unless you have super high voltages, dangerous but fun to watch Electroboom, where air will become a conductor.
Air will become a conductor. That is a truly terrifying sentence if you sit and really think about it.
It is the literal definition of lightning. It is the definition of an industrial arc flash. Aram understands that insulation isn't an absolute magical property. It is highly conditional. Air stops 1.5 volts from a tiny AA battery. Air absolutely does not stop 300,000 volts leaping from a transmission line.
This concept, what is the technical term for it? Dielectric breakdown.
Yes. Every single insulating material in the universe has a breakdown voltage. It's the breaking point where the electrical pressure is so overwhelmingly strong that it physically rips the electrons right off the atoms of the insulator itself. It turns the air into plasma, and plasma conducts electricity very well.
So when you or I flip a light switch in our living room, we are completely relying on the fact that the 220 volts on the wall just isn't strong enough to jump the tiny physical gap we just created inside the plastic housing.
Exactly. If you had 10,000 volts running through your drywall, flattening that regular switch to off wouldn't turn the light off. The electricity would just violently arc right across the open switch contacts with a loud buzz and a blinding flash of purple light.
This kid is in grade 6?
Apparently. And he thinks watching that happen is fun to watch.
This leads perfectly into part 4. Conductors versus insulators.
Mm.
The textbook has a very binary black and white view on this.
It does. It has to for that introductory level. It says, conductors allow current to pass. Examples, copper, iron, aluminum. Insulators do not allow current to pass. Examples, wood, rubber, glass, cotton, plastic.
It explains that this is why wires are made of copper for efficient transport and why they are covered in plastic for your safety.
Standard safety protocols. It creates a neat little world of safe and unsafe. Touch the plastic, don't touch the shiny metal.
But Aram has already poked a massive hole in this with his previous comment about the air gap. He has another note right here, specifically labeled a lateral note in all caps.
He writes, most people all think that something is a conductor or an insulator, and that is not true. Everything is a conductor at high enough voltages, and everything is an insulator at low enough voltages.
That is profoundly philosophical for a margin note in a physics textbook.
It's acknowledging the gradient of reality. He is actively challenging the binary system the book is trying to teach him.
Can you explain that a bit more? Everything is an insulator at low enough voltages.
Sure. Even copper, which is the best commercial conductor we use commonly, has some inherent resistance. It isn't perfect. If you have a voltage that is incredibly, infinitesimally small, even copper might look like a roadblock. But the more important and dangerous part is the other side of his statement. Everything is a conductor at high enough voltages. If you hit a tree with a massive bolt of lightning, it conducts. It usually explodes because the sap boils instantly, but it definitely conducts the current to the ground. You can arc electricity right through solid glass if the voltage is high enough. You can arc through thick rubber. This is exactly why specialized electricians who work on high voltage power lines wear incredibly thick, specially rated rubber suits, not just the yellow rubber gloves you use to wash dishes. They need significantly more insulation thickness to hold back that higher electrical pressure.
So Aram is essentially telling us, don't get too comfortable just because you were wearing rubber-soled shoes.
Exactly. He is saying that safety is relative. It completely depends on the voltage you are dealing with.
This kid is going to be a brilliant electrical engineer. Or a terrifying supervillain, one of the two.
Let's really hope for engineer. He clearly has the deep curiosity for it.
Speaking of engineering, let's move on to part 5, solar energy and DIY engineering. The text briefly touches on solar cells.
Right. Using sunlight to generate current directly. It mentions calculators, solar cookers, street lamps, satellites in space. It's the standard clean energy angle.
But Aram isn't as interested in the passive solar panels. He is interested in the active circuitry. He mentions a digital tool he uses.
Every circuit. It is a very popular app and website for simulating electronic circuits visually.
He writes, in back Aram, usually when I make circuits, yes I do, I have made a half-bridge rectifier, boring, and a full-bridge rectifier with 3 smiley faces.
I love the clear distinction he makes. Half bridge, boring, full bridge, absolute joy.
For you listening who perhaps hasn't built a rectifier in your garage lately, what exactly is he talking about? What is a full-bridge rectifier?
So remember we talked briefly about AC, alternating current, and DC, direct current.
Yes.
Batteries are DC. The electrons flow smoothly in one single direction, like water in a river. The power from your wall outlet is AC. The electrons jiggle back and forth 50 or 60 times every single second.
Like a hand thaw.
Like a saw, back and forth, push and pull. Now, most sensitive electronics, your phone, your computer, the LEDs we talked about, they all need DC. They need a steady, calm river, not a violent saw. A rectifier is a specific configuration of components that converts that AC into DC. It rectifies the messy current.
Okay, so what is a half-bridge?
A half-bridge rectifier basically just blocks half of the AC wave. Think of a one-way check valve in a pipe. It lets the water go forward, but when the water tries to reverse and go backward, it just completely stops it. So the output you get is a pulse of power, then nothing, then a pulse, then nothing.
That sounds incredibly inefficient.
It is. You are literally throwing away half of the electrical power the utility company is sending you. It is boring, exactly as Aram says.
And the full-bridge rectifier.
A full-bridge rectifier uses 4 diodes arranged in a specific diamond shape. It is a piece of brilliant electrical geometry. It takes the forward flow of the AC and lets it pass normally. But when the current reverses and tries to flow backward, the diodes gracefully ride it around a different path so it also comes out the other side, flowing forward.
So it takes the negative backward half and flips it.
It flips it right up. You get pulse, 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 pulse. A continuous stream of forward energy. You use all the energy from the wall. It's elegant. It's incredibly satisfying to build and watch work.
So he's excited about the geometry and the efficiency.
And he's excited because Electroboom, the YouTuber he clearly watches religiously, is famously obsessed with full bridge rectifiers. It is a massive inside joke, a meme in that engineering community, but it's also very real foundational engineering. Aram is simulating these things safely on his computer, so, as he explicitly says, he can explore electricity without getting choked. XD.
XT. A laughing face. He knows exactly what the danger is.
He deeply respects the danger. Software simulation is the safe place to fail catastrophically.
Which brings us to the final and perhaps most intense section of this deep dive, Part 6. Safety first and last.
The textbook is very responsible here, as you would expect. It lists the cardinal rules.
Rule 1. Never touch electrical devices with wet hands.
Water, especially tap water loaded with minerals, is a great conductor. It dramatically lowers the natural electrical resistance of your skin, making it far easier for a deadly shock to enter your body and reach your vital organs.
Rule 2. Wear rubber-soled footwear.
This isolates you from the ground. If you are electrically insulated from the physical earth, the current has nowhere to go. It can't flow through you to get to the dirt. That's why birds can sit safely on high-voltage power lines, because they aren't touching the ground to complete the circuit.
Rule 3. Fire safety. Never use water on electric fires. Use a proper fire extinguisher or switch off the mains immediately.
Critical life-saving advice. Tossing water on an electrical fire just spreads the conductive path. You might electrocute yourself through the puddle while you're just trying to put out the flames.
Rule 4. No playing. Do not experiment with home sockets.
And this is exactly where Aram gives us his final warning. And honestly, it is the most vivid, visceral description of electrocution I have read in a long time.
It really is. He's not just saying, oh, it's dangerous, stay away. He is giving us the exact technical specs of the danger.
He writes, do not play with electrical sockets. They have AC correct at, I think here it's 220 VAND 50 HZ.
220 volts? 50 hertz? He knows his local power grid specs by heart?
And he explains scientifically why that specific combination is so uniquely bad, he says, which will, kind of stun your body and will make it so I can't let go.
AC will make it so I can't let go.
Oh.
That is referring to the Titanic contraction.
Exactly. This is the true physiological nightmare of alternating current. A high-voltage DC shock often physically kicks you away. A single massive muscle spasm throws you back across the room. It hurts immensely, but you are quickly disconnected from the source. Alternating current cycles back and forth 50 times every single second. That's the 50 hertz. That electrical signal violently interferes with your own body's nervous system. It artificially tells your muscles to contract 50 times a second. Your hand involuntarily clamps shut around the wire. You physically, biologically, cannot open your hand to drop it. You grip the live wire tighter.
That is literally the stuff of nightmares.
It is. It's technically called the let-go threshold, or the can't-let-go current. And because you are trapped holding it, the duration of the electrical exposure is much, much longer.
And Aram finishes the thought with a brutal description. He says, and then it will fry you from the inside.
Fry you from the inside.
That sounds like a dramatic line from a sci-fi movie, but is it medically accurate?
Sadly, it is completely accurate. The human body acts as a resistor in the circuit. When electric current flows forcefully through a resistor, it creates heat, just like the tungsten filament in the light bulb we discussed. If you are gripped onto that wire, your internal tissues, your delicate nerves, your blood vessels, they all start to rapidly heat up. You literally burn from the inside out.
And then he quickly adds the legal disclaimer. He writes, and this has not happened to me, and I'm not planning to do this.
I fully believe him on the not planning to do this part. I am highly skeptical on the not happened to me part. He describes that stun feeling just a little too accurately. Kind of stun your body. That's experience talking.
I think Aram has definitely had a minor run-in with the mains at some point, or at least a very, very spicy capacitor from disposable camera.
But look at the educational value of what he's done here. He's taken a boring, standard rule, don't touch sockets, and he's given you the actual mechanical breakdown of the danger. He's explained the frequency, the voltage, the terrifying muscle reaction, and the gruesome thermal consequence. He has made the safety rule sticky because he made it absolutely terrifying.
It is incredibly effective education. Fear is a fantastic teacher.
It truly is.
So we have reached the end of the chapter. We have gone all the way from the basic definition of energy flow to the specific chemistry of zinc and copper cells. We have seen the historical transition from hot tungsten to cool LEDs. We have learned that insulator is just a temporary word we use for things that haven't been shocked quite hard enough yet.
And we have met Aram.
We have. And I think that is the real lasting takeaway here for you. You have the source, the textbook. It's structured, it's safe, it's technically correct. But then you have the learner. The learner is messy. The learner is making jokes about calm cleaners in the margins. The learner is building full bridge rectifiers in a software simulator and spending his free time thinking about how the invisible air turns into a conductor.
It deeply reminds us that real learning isn't just passive absorption of facts, it's active synthesis. Aram is taking the textbook, taking his YouTube videos, taking his own slightly dangerous experiments, and mixing them all into a mental worldview that is actually far deeper than the book itself provides.
He is engaging with the material, he's arguing with the definitions, he's updating the obsolete tech.
He is a scientist in training. Questioning the foundational definitions is what scientists do.
Before we sign off, I really want to leave you with a final thought to mull over, based entirely on Aram's lateral node.
But what about the air gap?
Yes. We walk around every single day assuming the air around us is just empty space. It's neutral. It's safe. It is just the absence of physical things. But Aram reminds us that under the right conditions, with enough electrical pressure, enough voltage, the very air we breathe can violently turn into a wire, a temporary path for fire.
It makes you look at a heavy lightning storm quite differently. It's not just pretty flashes of light in the clouds, it is the sky physically breaking down. It's the atmosphere failing to do its job as an insulator.
And it makes you look at that little plastic light switch on your living room wall differently. It is the only thing standing between you and the 220-volt monster in the wall that wants to grab your hand and never let go. It's just a tiny, fragile gap of air that keeps the monster trapped in the copper.
So definitely check your plastic insulation.
And maybe don't try to build a full bridge rectifier unless you really, really know what you were doing.
Very wise words.
Thanks for listening to this deep dive. And Aram, if you are out there listening, keep annotating your textbooks.
And please, stay safe.
We will see you next time.